In this video, we'll talk about the mean value theorem for derivatives and some of its consequences. We'll start by a statement of the mean value theorem. The mean value theorem states that if f is a continuous function on a closed interval from a to b, and differentiable inside of that interval, then there is at least one number c between a and b such that f prime of c is equal to f at b minus f at a over b minus a. One way to think about this theorem is to think about it in terms of slopes of lines. The quantity on the right side of this equation, f at b minus f at a over b minus a, is the slope of a line passing through 2 points on the curve, namely the endpoints over this interval, the points with coordinates a, f at a and b, f at b. If you draw a secant line through those 2 points, then the slope of that line will be the difference of the y's over the difference of the x's, which is exactly this quantity on the right. The quantity on the left, f prime of c, is the slope of a tangent line. What the theorem is saying is that there is some number between a and b where the slope of the tangent line is the same as the slope of the secant line passing through the 2 endpoints over the interval. And that's what we see here. We have the same curve as before, and we have the line passing through the endpoints. All of the lines pictured here have the same slope. They're all parallel. That means there isn't just one point C between A and B where the tangent line has slope equal to the slope of the secant line through the endpoints, but in fact we have 1, 2, 3. So there might be more than one number c between a and b that satisfies the conclusion of the mean value theorem. What the mean value theorem is telling you is that there's at least one point between a and b where this happens. We can think of the derivative as a rate of change. So if we imagine that f of t represents the amount of a quantity after t units of time, then f prime of t represents the instantaneous rate of change in the quantity after t units of time. And in this case, the quotient f of b minus f of a over b minus a represents the average rate of change in that quantity between t equals a and t equals b. We could, for example, imagine that f of t represents displacement, in which case f prime of t would represent velocity. And so what the mean value theorem states in this case is that there's a time between a and b where the average rate of change, that is, the average velocity in our example, is equal to the instantaneous rate of change, or the instantaneous velocity. Let's look at a real-world example. Tradition has it that the southernmost point of mainland England is Land's End in Cornwall, and the northernmost point of mainland Scotland is John O'Groats in Caithness, so that a journey from Land's End to John O'Groats is popularly thought of as traversing Great Britain from its southernmost point to its northernmost point. It is not uncommon for events to take place between the two locations. The last record holder for solo motorcycling from one to the other was Ivan B. Hart Davis in 1911, who traveled the 886-mile distance in 29 hours and 12 minutes. So why is that the final record, you might ask? Well, the Auto Cycle Union banned further record attempts after they computed his average speed. 886 divided by 29.2. 29.2 hours is 29 hours and 12 minutes. If you compute that, 886 divided by 29.2, that's approximately 30.34 miles per hour. And that meant that at some point he exceeded the then maximum allowed speed of 20 miles per hour. This was in 1911, and so speed limits were much lower at the time. But this is a real-world example of the mean value theorem because his average speed was 30.34 miles per hour, and that meant that at some point during the journey he must have exceeded the speed limit of 20 miles per hour. What you see here is an example of what a distance curve might have looked like. Now, we don't actually know what his position function or distance function was, but what we do know is that if we have s of t giving the distance traveled after t hours, then its derivative gives the instantaneous speed after t hours. So if you graph some function that might give you the distance, so this is some curve that describes distance traveled up to 886 over 29.2 hours, then we know what the average velocity was. That's the slope of the secant line connecting the two endpoints of this curve. And we know what the slope of this secant line is. It's at least approximately 30.34. And we can see that there are actually several different places along this curve where the slope of the tangent line is the same as the slope of the secant line. That is, where the tangent line is parallel to the secant line. If we were to zoom in right about here, we'd get this picture. And you can see that the secant line, or at least a portion of it, appears right here. So if we were to just draw in a line that was parallel to that secant line, we can move this around and we can see that there is a place where it intersects the curve, right there. So at this point in time, approximately, the instantaneous velocity is 30.34. And we can actually see that there are multiple places where that happens. There's one right down here, one right here, one right here, and one right here. So we can see that there are actually several different places where the slope of the tangent line is the same as the secant line through these two endpoints. The mean value theorem just confirms what we can see visually, and that is that there must definitely be such a place between the two endpoints where the slope of the tangent line is the same as the slope of the secant line. The mean value theorem guarantees that yes, there will always be at least one such place. Let's look at an example. Let f at x equal 1 over 1 plus x. Find a value c between 1 and 5 for which f prime of c equals f at 5 minus f at 1 over 5 minus 1. So what this problem is asking us to do is find some number c which satisfies the conclusion of the mean value theorem. Now before we can do that, we need to actually compute what this quotient is. So let's go ahead and do that. So let's just compute all of the pieces. So we need f at 1, and that's equal to 1 over 1 plus 1 is 1/2. And f at 5 is 1 over 1 plus 5 is 1 over 6. So now we want to compute this quotient. So we're going to compute f at 5 minus f at 1 over 5 minus 1. And so that will be f at 5 is 1 over 6, minus f at 1 is 1/2, and divided by 5 minus 1 is 4. So we want to give these a common denominator. So we just multiply 1/2 by 3 over 3. And that will give us 1 over 6 minus 3 over 6 divided by 4, which is equal to minus 2 over 6 quantity divided by 4. And if you reduce that, you'll end up with minus 1 over 12. Now we want to find some c so that the derivative at c is equal to this value, negative 1 over 12. Well, in order to do that, we need to know what the derivative is. So we want to compute the derivative of f. So f at x, let's just rewrite it as 1 plus x to the negative 1. This is a composition, so it's something raised to the negative 1. So f prime of x is minus 1 times 1 plus x to the negative 1 minus 1, which is the negative 2, and then we have to multiply by the derivative with respect to x of whatever was inside there, which in this case is 1 plus x. So 1 plus x is our inside function. So you use the power rule, the minus 1 comes down here, and then it's minus 1 times whatever's inside raised to the negative 2 times the derivative of whatever's inside. Now the derivative of whatever inside that's the derivative of 1 plus x, which is just 1. So we just end up with minus 1 over 1 plus x quantity squared. Now our objective is to find some value where this is equal to minus 1 over 12. So we want to find, can we find some value for x where that's true, and that will be our value for c. So the first thing we can do is observe that if this equation is true, if minus 1 over 1 plus x quantity squared is equal to minus 1 over 12, then the denominators have to be equal to each other. So you have a minus sign here and a minus sign here, so run a minus sign through both sides, then look at the reciprocals. So we have to find an x such that 1 plus x quantity squared is equal to 12, and this is easy enough to solve. You just compute the square root of both sides, and you'll have 1 plus x is equal to plus or minus the square root of 12, and so x is equal to minus 1 plus or minus the square root of 12. So we have that x is equal to either minus 1 minus the square root of 12, or x is equal to minus 1 plus the square root of 12. This first one here, this is a negative number. It's definitely not between 1 and 5, so that means our solution is this. So this is going to be our value for c here. Minus 1 plus the square root of 12. We know from the mean value theorem that there must be some value, at least one value c, for which this is true, and now we found it. Let's do another example. Let f of x be equal to x plus x squared over 2 minus x cubed over 3. This is a polynomial. That means it's continuous everywhere, it's differentiable everywhere. Verify that there is a value c between minus square root of 3 and positive square root of 3 for which f prime of c is equal to f at the square root of 3 minus f at negative square root of 3 divided by the difference between the two, which is 2 square roots of 3. So again, we want to verify the conclusion of the mean value theorem for this function f, and we're looking at an interval from minus square root of 3 to positive square root of 3. So minus square root of 3, this is our a in this example, and positive square root of 3, this is our b. Okay, well, we need to actually work out what this quotient is, so we can do that. So f at square root of 3 is equal to the square root of 3 plus the square root of 3 squared, so that's 3 over 2, minus the square root of 3 cubed, so that's 3 square roots of 3 over 3. And so you'll notice that this 3 cancels with that 3, and then we have the square root of 3 minus the square root of 3, so that's just going to give us 3 halves. F at the opposite of square root of 3 is going to have a similar value. In fact, it'll be the same. So this will be minus the square root of 3 plus, and now negative square roots of 3 quantity squared, that's 3 again, 3 over 2. And then it's going to be minus, and then it's a negative square root of 3 cubed, so that's going to give us a negative 3 square roots of 3, and all of that is over 3. Let's just put some parentheses around that. And now you get the same sort of thing. You have that minus cancels with that minus, that 3 cancels with that 3, and then here you have the opposite of square root of 3 plus the square root of 3. Those will cancel, and you're just left with 3 halves. So if we go back to this quotient here, this is just going to be equal to 3 halves minus 3 halves over 2 square roots of 3, which of course is just 0. So we're actually looking for a place where the derivative is equal to 0. Well, what is the derivative? So we know what f is. Let's just rewrite it. F at x is x plus x squared over 2 minus x cubed over 3. So if we compute the derivative f prime of x, that's going to give us 1 plus 2x over 2 minus 3x squared over 3. And of course, again, your constants will disappear here, and you're just left with 1 plus x minus x squared. So we want to find some value for x where this is equal to 0. So can we find such a value of x? Well, yes, we can. We just use the quadratic formula. So we have that, let's just rewrite this, minus x squared plus x plus 1 equals 0. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. And if we simplify this, we'll have minus 1 plus or minus the square root of 1 plus 4 is 5. And all of this is divided by negative 2. So what that tells us is that x is equal to either 1 plus the square root of 5 over 2, or x is equal to 1 minus the square root of 5 over 2. Notice that there's a minus here and a minus here, so that's why this is a positive 1 over 2. Now, both of these values are within the range. This 1 plus the square root of 5 over 2 is slightly smaller than the square root of 3, and this number 1 minus the square root of 5 over 2 is slightly larger than negative square roots of 3. So both of these work. Now, some of you might be familiar with this number right here. This is the golden ratio, which is showing up in this problem for no particular reason. It just happens to be here. Let's talk about some consequences of the mean value theorem. The first one is what I'm calling here the zero derivative theorem, although I don't know that it really has a name. And the statement is that if f prime of x is equal to 0 for all x between a and b, then f is a constant function between a and b. So f is constant between a and b is what that should say. On the interval from a to b. Okay, the proof is quite straightforward. Just pick any x0 in this interval. Then by the mean value theorem, for any other x in that same interval, there exists some c between the two, x0 and x, such that this quotient, f at x minus f at x0 divided by x minus x0 is equal to the derivative. But the assumption is that the derivative is equal to 0 for all x between a and b. We know that x0 and x are both between a and b. So if we have some c which is between those two x values, then it must also be between a and b. So f prime of c is equal to 0. So we have that this difference of y values over the difference of x values is equal to 0. Well, as long as we choose x not equal to x0, so it probably should say by the mean value theorem for any x not equal to x0, such that x is not equal to x0, in that case, the denominator can't be 0. And so the numerator must be 0 because we have a quotient which is equal to 0. We have a quotient that's equal to 0, and the denominator isn't equal to 0. So that means the numerator must be equal to 0. So that tells us that f at x minus f at x0 is equal to 0. So f at x must be equal to f at x0. So we just picked any x between a and b, well, such that it wasn't actually equal to x0. And the conclusion, so if you pick some x between a and b, which is not equal to x0, then you get that f at x must be equal to f at x0. But of course, if x is equal to x0, then f at x0 is equal to f at x0. It's equal to itself. So what we have is that f at x is equal to this value, f at x0, for all x between a and b, and therefore it's constant there. So this actually has some useful consequences. As sort of an obvious example, I suppose, we can use this to show the Pythagorean identity, which is something that we already know from the way that we define cosine and sine. But we can use this as a basic example to show how this theorem can be used. So let's start by letting f at x be equal to cosine of x, quantity squared, plus sine of x, quantity squared. And we want to show that this is always equal to 1. Well, in particular, that means it must be constant. So we can show that this is true by computing the derivative. F prime at x is equal to, well, it's the derivative with respect to x of cosine x quantity squared plus the derivative with respect to x of sine of x quantity squared. Just differentiating term by term. So the first one, the derivative of cosine squared, that's going to be 2 times cosine of x to the 1 times the derivative with respect to x of cosine of x, plus the second derivative. So again, we're using the power rule here. Notice this was something squared. So the derivative of something squared is 2 times that thing to the 1 times the derivative of that thing. Now we're going to do the same thing to this next derivative. The derivative of sine squared, that's the derivative of something squared, so that's 2 times that thing to the 1 times the derivative with respect to x of whatever that thing was. In this particular case, that thing was sine of x. But of course, what is the derivative of cosine of x? It's the opposite of sine of x. And the derivative of sine of x is cosine of x. So we have that f prime of x is equal to 2 times cosine of x times the opposite of sine, so let's put the minus sign in front, times sine of x plus 2 times sine of x cosine of x. And here we have the opposite of 2 times sine times cosine plus 2 times sine times cosine. These cancel, and we have that f prime of x is equal to 0. Now this was true for all x. So f prime of x is equal to 0 for all x. So by the zero derivative theorem, f at x is equal to some constant for all x. And to figure out what the value of that constant is, you just pick some x value. So f at 0 is equal to cosine of 0 squared plus sine of 0 squared. Well, cosine of 0 is 1 squared plus sine of 0 is 0 squared is equal to 1. So that tells us that our constant is equal to 1. Now we could have picked any number at all and put it in here because we just showed that f at x was equal to constant. So that means for any x that you plug in, you're just going to get the same output. So we can pick any x that we want. So you just pick a convenient x. And a very convenient x is usually x equals 0. So we just pick x equals 0, plug it in, and see what we get. We get a 1. But we would have gotten the same constant if we plugged in any x. So what that tells us is that f at x is equal to 1. But what was f at x? It was cosine of x squared plus sine of x squared. So that means for any x, cosine of x squared plus sine of x squared must equal this constant 1, which is exactly what we wanted to show. Let's look at another consequence of the mean value theorem. This is called the constant difference theorem. Well, this is actually a consequence of what we just showed. So the statement of the theorem is that if f and g are differentiable on some interval from a to b, and they have the same derivative on that interval, so f prime of x is equal to g prime of x for all x between a and b, so they have the same derivative on an interval, then there must be some constant c such that f at x is equal to g at x plus c for all x in that interval. In other words, if two functions have the same derivative on an interval, then they differ by at most a constant. And this is very easy to prove because we just used the zero derivative theorem from an earlier slide. So we start by inventing a new function that we call h. And h is just the difference between f and g. We're measuring the difference between f and g. Now the claim is that h is constant. So we know that f and g have the same derivative. So if you differentiate h, then that's just going to be h prime at x is equal to f prime at x minus g prime of x. But we're assuming that f and g have the same derivative, so this has to be equal to 0. Well, by the zero derivative theorem, that tells us that h is constant. So there's some c such that h at x is equal to c for every x. But what was h? H was the difference between f and g. So f minus g is equal to some constant for any x. And so then you just add this g at x to both sides, and then you have f at x is equal to g at x plus c for all x in a to b. for all x in the interval from a to b. Let's take a look at an example of this. And again, we'll just do a simple example. But suppose that we have a function f at x, which is ln of 5x. What's the derivative of ln of 5x? Well, it's a composition. It's ln of a thing. So the derivative of f with respect to x is the derivative with respect to x of ln of a thing. But using the chain rule, the derivative of ln of a thing is 1 over that same thing. So the derivative of ln of a thing is 1 over that thing times the derivative of that thing. But the derivative of 5x is 5. So what do we have? We have 1 over 5x times 5. The 5's cancel, and you're just left with 1 over x. And of course, 1 over x is the derivative of the natural logarithm of x. So f at x has the same derivative as ln of x. So that means that ln of 5x differs from ln of x by at most a constant. But actually we know this already because of the properties of logarithms. ln of 5x is equal to ln of 5 plus ln of x, because the property of logarithms that we're using here is that it turns products into sums. So ln of 5x is a constant plus ln of x. So if you differentiate both sides of this equation, the derivative of a constant is 0. So the derivative of ln of 5x is equal to the derivative of a constant, so that's 0, plus the derivative of ln of x. So that's why they have the same derivative. And now we have a very significant theorem, the increasing-decreasing function theorem. Well, function theorems, really. It's 2 theorems in one. So the first one is that if f prime of x is strictly greater than 0 for all x between a and b, then f is an increasing function on this interval. So if the derivative is positive on an interval, then the function is increasing on that interval. And similarly, if the derivative is negative on an interval, then the function is decreasing on that interval. This is really easy to believe because if a function has a positive derivative, that means its rate of change is positive. So that means it's increasing. And if a function has a negative derivative, that means its rate of change is negative. So if something is changing negatively, that means it's decreasing. So it's believable that the function is decreasing. You can also think of this in terms of slopes of tangent lines. So if you have a positive slope, then that means the function should be increasing there. And if you have a negative slope, then it's believable that the function is decreasing because the tangent lines are increasing or decreasing. Anyway, this theorem follows directly from the mean value theorem. So just let x1 and x2 be any two numbers in this interval. One of them has to be smaller than the other, so let's just assume that x1 is less than x2. Then by the mean value theorem, there's some c between x1 and x2. So x1 is less than x2, so there's some number between them, such that the difference of the outputs, f at x2 minus f at x1, divided by the difference of the inputs, is equal to f prime of c. This is just the mean value theorem. Now, if we're assuming a, if we're starting with a, then that means the derivative has to be positive. So if this value is equal to the derivative, and that derivative is positive, then that means that the numerator must be positive. The denominator is definitely positive. x2 is bigger than x1, so the denominator is positive. If we assume that the derivative is also positive, then that means the numerator must be positive. So f at x2 minus f at x1 is positive. Well, that just means that f at x2 is greater than f at x1. And that means that f is getting bigger, so it's an increasing function. Remember, this is true for any x2 greater than x1. Now, if we look at b, then that means the derivative is negative. So if we assume that this derivative is negative, well, x2 minus x1 is still positive. So the denominator is positive, but the value is equal to a negative number, so that means the numerator must be negative. So f at x2 minus f at x1 is less than 0, so f at x2 must be less than f at x1. So that means the function is getting smaller. So the function is decreasing, at least on this interval. We only know that the derivative is negative on this interval, so that means the function is decreasing on that interval. Let's look at an example here. The function f at x equals x squared. Well, that's this parabola right here. What is this dashed line? This dashed line is the derivative. What do we know about the function f at x equals x squared? Well, it's decreasing until you get to the valley at x equals 0, and then it's increasing. Well, the derivative, so this function here, this graph, this solid graph, this is y equals x squared. And the dashed graph is the derivative. This is y equals 2x. And what do we know about it? Well, it's negative whenever x is negative. So as long as x is negative, the derivative is negative, and you can see that the function is decreasing here. Now on the interval from 0 to infinity, where x is positive, the derivative is positive, so that means the function is increasing. And again, you can think about this in terms of tangent lines, because any place where the function is decreasing, you'll have a tangent line with negative slope. And negative slope just means that things are getting smaller as you move to the right. And if you're where the function is increasing, you can see that the tangent lines have positive slope. And a line having positive slope just means that the outputs are getting larger as you move to the right. And so if the tangent line is positive for all values of x on an interval, then the function will be increasing there. Now notice that the theorem doesn't tell us anything about what's going on at 0. That's because the derivative is neither positive nor negative there, it's 0. So on any interval to the left of 0, you have a negative derivative, so the function is decreasing. And on any interval to the right of 0, the derivative is positive, so the function is increasing. But the theorem doesn't tell you anything about an interval that actually contains 0. Let's up the exponent by 1. So now we're looking at g at x equals x cubed. So once again, we have a solid graph here, and that's y equals x to the 3. And we have a dotted blue graph, and that's the derivative. That's y equals 3x squared. Now 3x squared is never negative. It's always positive away from 0. And you can see that on this blue dashed graph. It's always non-negative. So on any interval not containing 0, you'll have a positive derivative, which means the function is increasing there. And you can see that. On any interval not containing 0, the function is increasing. Well, in fact, the function is increasing even on any interval containing 0, because if you pick any interval at all, the function is increasing. It's just that the derivative doesn't tell you that. The function is increasing everywhere, but the derivative only tells you that it's increasing away from 0. That's because the derivative is 0 at 0. So this is what we mean when we talk about derivatives giving you local information. Because if you're sitting on x equals 0, the graph is quite flat there. So the derivative can't tell that the function is not constant. Sitting at x equals 0, the derivative is 0, so the derivative says, oh, I guess this is a constant function. It's actually not. It just looks like it when you're sitting there at x equals 0. So that's why this increasing, decreasing function theorem, based on information about the derivative, fails to tell you anything useful at 0. But as long as you're away from 0, the derivative is strictly positive, and so the derivative tells you that the function is increasing on any interval not containing 0. It just so happens that in this case, it's also increasing on any interval containing 0, but the derivative can't tell you that. Here's another example. The function h at x equals e to the x. Well, in this case, e to the x is its own derivative. That's why you only see one graph here. The function and its derivative are the same, so you can only see one graph. Now, notice that e to the x is always positive on any interval. So that means that the function e to the x is increasing for all x, which we can see that it is. And in fact, if you draw any tangent line in at all, it will have a positive slope, indicating that the function is increasing around that point of tangency. And in fact, it's increasing everywhere. Here's a function which is a little bit more involved. K at x equals x times e to the negative x. So again, the solid graph is the graph of the function. So this is y equals x e to the negative x. Whereas the dotted graph, or the dashed graph, is the derivative. So this one here, this is y equals the derivative, which you can compute, and you can see that it's 1 minus x times e to the negative x. So this function, the function, is increasing until you get to x equals 1. And that's because the derivative is positive until you get to x equals 1. So remember, the dashed blue graph is the derivative, and the derivative is positive until you get to 1. So that means our original function, which is the solid graph, is increasing until you get to 1. But then the derivative becomes negative. So after that point, your function is decreasing. So the function is increasing while the derivative is positive, and then as soon as the derivative becomes negative, after 1, the function is decreasing. So this gives us a nice way to determine where the function changes from increasing to decreasing. And why might that be valuable? The place where the function changes from increasing to decreasing, well, that's the maximum value of the function. So if this function was giving you some quantity and you wanted to know when that quantity was maximized, well, it happens precisely when the function changes from increasing to decreasing. So it happens when x is equal to 1. And this is something that we'll encounter again when we use the derivative to compute the maximum and minimum values for a given function.